In this video, we will be discussing the evolution and development of cetaceans, better known as the whales, that resulted in a land-to-sea transition reversing millions of years of sea-to-land development.
The Indahyus, part of the family Rheolidae in order Artiodactyla from 45 to 55 million years ago in the Eocene, showed early similarities to extant cetacea, being through its behaviour, where it would enter the water for short periods of time. Indahyus had a more carbon-13 in enamel compared to whales, indicating a more terrestrial plant-based diet, making it clear that entering water was a predator avoidance mechanism and not for fish.
Wait, surely its vertical range is limited by the lack of evolutionary adaptations such as flippers and enlarged lung capacity, no?
Yes, that's right, they did lack these. However, Indahyus did have the involucrum bone in the middle ear to aid in underwater hearing, being the only appearance of a cetacean diagnostic feature in another mammal. An abnormal lung capacity allowed up to 4 minutes underwater with movement and sinking like a hippopotamus, aided by denser bones. Denser or thicker bones is also seen in early whales like Pakicetus and Ambulocetus. So although extinct cetacea that diverged from Indahyus have these features, we see that Indahyus is an ancient link to whale origins. Next we have the family Pakicedae, which emerged in the Eocene about 47 million years ago and are classed as the oldest whales due to fossils discovered from after the cetacea-artiodactyl divergence. They had sharper teeth with enamel wear patterns correlating with fish eating, as well as their eyes having a heterotopic movement to the top of the skull to see above the waterline.
How come there isn't any clear aquatic adaptations yet?
While the Ambulocetus, found 49 million years ago, were more aquatic, they had sideways-facing eyes showing ambush tendencies and enhanced hearing from a larger lower jaw, showing how extant cetacea use fat in the jaw to transmit sound to the ears. Darcy-Thompson's transformation theory of coordinated characteristic change is seen here with its slim body and short limbs. Webbing also starts to appear as reduced apoptosis at interdigital regions occurs from the lower BMP activity. Myoglobin upregulation could have also started here, which is known to increase dive times in extant species.
Is there any more families before the extinct cetacea?
Only 3 more. The Remingtonocetidae, 48 to 41 million years ago, seen development in the hearing structures with the beginnings of an immobile neck, thus smaller semicircular canals, to avoid overstimulation from acrobatics. They also had a long snout. Another family, Protocetidae at this time, had larger eyes and signs of posterior nostril migration, which gives rise to the blowhole in extant species. Developmental repatterning was a result of them inhabiting other oceans, facing different selection pressures. Protocetidae, like Rhodocetus, had developed hind limbs with the pelvis not connected to the spinal column, so its weight couldn't be supported on land. This foreshadows the pelvis as now a vestigial structure. Finally, the Basilosauridae emerged 41 million years ago, being classed as the first fully aquatic cetacea. They had a blowhole, flippers, a fluke, and small hind limbs. They had heterodont dentition, meaning different types of teeth to aid in hunting. Individual forelimb digits also aren't visible due to intense webbing as well as greatly reduced hind limbs. They also had peripheral vasoconstriction to avoid hypoxia and oxygenate organs from 3 non-synonymous mutations in 2 vasoconstrictor genes. Being now fully marine, Basilosauridae must have had complete loss of the SLC4A9 gene, meaning loss of saliva production, this being a dispensable trait when fully marine. Ancient cetacea also had 2 amino acid substitutions in the HOXD11 gene that regulates limb development and thus explains hind limb loss through carpal and tarsal reduction.
Now for extinct species, starting with the divergence of baleen and toothed cetacea. The divergence of teeth to baleen occurred around 34 million years ago. This formed the 2 groups, Mystaceti, possessing baleen for filter feeding, and Odontoceti, all being toothed whales. Mystaceti genes for enamel formations like ameloblastin and enamelin are still present today. However, these have degraded into pseudogenes from inactivating frameshift mutations and SOC codons. These pseudogenes still cause tooth buds in fetal stages of the Mystaceti. However, they are soon lost through baleen plate formation.
Are there any unique adaptations in the Odontoceti?
Yes, the Odontoceti gained adaptations like increased fat synthesis causing development of the melon and fat on the lower mandible. Both of these structures allowed for effective echolocation, which is now used for hunting and communication.
Is hair and limb development still different to terrestrial mammals?
Yes, extant cetacea retain hair follicles in utero, with only some species possessing whiskers when mature. Positive selection for FGF5 gene promoted the hair growth termination. This caused less hair to form, thus reducing drag, improving abilities to catch prey. Further genetic evidence suggests that cetacean hairless gene, HR, became a pseudogene, leading to its dysfunction and therefore causing hair loss. Extant cetaceans lost hind limbs around 34 million years ago, possibly caused by the loss of sonic hedgehog signaling. Reduced expression of sonic hedgehog restricted the formation of both apical ectodermal ridges and zones of polarizing activity, both required for limb bud development. Scientists discovered that an upstream regulator of sonic hedgehog, HAN2, was absent in extant whales, causing less sonic hedgehog expression. Hind limb buds are found in early fetal stages. However, limb buds arrest and degenerate around the 5th gestational week due to the absence of sonic hedgehog. Forelimbs were also altered due to the changes in sonic hedgehog expression and its associated signaling pathways. TBX4 and TBX5 are genes that are both crucial in the forelimb development. Differing expression of these genes during embryonic development may have altered fallen morphology. BMP signalling pathways, possibly including gremlin gene, might have also influenced the fallen development as well. The upregulation of gremlin gene inhibited BMPs, causing webbing to form between the digits of the forelimbs.
All of these evolutionary and developmental processes have aided with the reversal of millions of years of sea-to-land transition events, forming a lineage of mammals inhabiting the global oceans.